So we've been working on systems of solutions for systems of nonlinear equations, and we're trying to solve them from the methods that we've learned in this class. So before we got started, we talked about continuity of our functions that are nonlinear. So given any function f of x, and if somebody wants you to comment on the continuity of these functions, the first thing you'd want to do is you'd want to write down the different values of your function. So if the function is sine of x, so this function basically gives you the sign of the function of the input x. So the function takes values +1 if x is greater than 0, -1 if x is less than 0, and 0 when x is equal to 0. It extracts the sign of the input.
Oh, okay.
Yeah. Which is a standard term in when you get on to do machine learning and stuff like that, they use a variation of this function. So it's a very important function, so you should know what it's called. Next thing to do would be you'd want to plot that function if you're going to look at the naive explanation of what continuity means. So if continuity was just defined as if you could draw a function where you can plot it without lifting your pencil, then you should be good. For a function like this, you get one segment like that at -1. At 0, your value is 0. Closed interval, open interval. And then when you're positive, the function returns 1. So this is +1, this is -1, and 0. In the definition of our function, by the definition of continuity, in fact, we can say that because you have to lift your pencil to draw the function like that, the function is indeed discontinuous. Similarly, let's take a more challenging example. Absolute value of x. How do you break down this function? Well, this function is f of x. It will take the value x if x is positive, and it will take the value -x if x is negative. How would we draw this? We know how to draw the absolute value of a function. It looks somewhat like this. Now, is this function continuous? Could we draw it without lifting our finger? Is it defined continuously? Yes, so it is continuous. Now, once you know if a function is continuous, the next question is it differentiable? Now, how do we check differentiability of a function? We know 3 definitions of differentiation, right? We know when we were numerically computing a differential, we know there's a left differential, there's a forward differential, there's a backward differential, there's a symmetric differential, right? But when we're talking about differentiability, we want to look at, so what is the slope of this variable? Let's say I take f of x, and I'm trying to determine if it's differentiable at x equals 0, right? What I will do is, from my forward difference method, I will say that my function from forward difference we say that the differential of x is given by x, the function at x, function at x plus h minus f of x by h, correct? Let's say my h is some 0.1, then my f of x plus h is f of 0.1 minus f of 0 by 0.1, and my value is 1, right? Then if I do backward, or let's just do symmetric so that we have a quicker. Symmetric difference, if I take, I get pocket works. Cool. I can stand up. Okay. From the symmetric definition, we know it is f of x minus f of x minus h by 2h, correct? My h is 0.1, so that becomes f of 0.1 minus f of minus 0.1 by 2 times 0.1. What does this become? F of 0.1 is 0.1, f of minus 0.1 is also 0.1 divided by 2 times 0.1, and that's 0. Are these comparable? Are these the same? No. So analytically, also limit of this differential, the left hand and the right hand limit of this differential will also be similar. So the left hand and the right hand differential will not be the same, and then you say, because these are not equal, f of x equals absolute value of x is not differentiable. At x equals 0. The more intuitive way to see that would be when I'm looking at the slopes, if the slope changes dramatically at a certain point, that means that the point there is not differentiable. Because this slope is going like that, and then at 0, this is another slope going like this, -1, +1, and then it should be around here, which is what the symmetric difference found. The 0 slope, this one is -1, and this one is +1, which is the forward difference. Because it's changing too drastically, we can say that the function is not differentiable, right? Now, why is that important? We'll come back to that once we do Jacobians and root finding, but we'll see why we're doing this. Let's say you had a more complicated function. Let's say you want to get, what does this function look like? Well, we know what sine looks like, right? Between minus pi to pi. Sine function looks something like, it'll go through 0, and it'll periodically be like this, right? This is sine of x. Now, how do I get x of sine x? That would just be just scaling of it, right? So like you'll happen to scale your sine wave according to where it is. So it'll be like this, right? And I'm thinking it's like, yeah, I'm terrible at drawing that part, but this will be f of x is x sine x. How do I know? We look at this and we multiply it by the value of x at each point, right? What does f equals x look like? It looks something like, I think it looks something like, will look like this. So basically, when this is multiplied by points on this, so this point multiplied by this point will be somewhere here, and this point with this point will be somewhere here, so it just scales according to this curve. So our sine wave is like increasing over time, right? Okay, now is this function continuous? Looks continuous. Do we see any sharp changes in differentials? No, so it is continuous and differentiable. Okay, now we know how to look at functions and say if they're continuous or if they're differentiable. The other thing about finding solutions is we look at algorithms. So the first one we did in class was bisection. The pseudocode for bisection is just that if you're given a function, so let's take this example problem. F of x is x cubed minus 2x squared plus 3. Now we may be able to find roots for it analytically, but let's see what the function looks like by plotting it in Julia. So this is x sine x, which is what we predicted, so we're right. Then, oh, actually, we got this part wrong, but that's because sine of minus x is negative and minus x is negative, so that becomes positive. But then let's look at this function that we're trying to solve for bisection. I plot that function between some arbitrary points of 3 and 4, which is the a and b in our algorithm. So the first thing we do in an algorithm is we define a less than b such that f of a times f of b is less than 0. So we need to identify an interval in which our root exists, which is a process in its own. Here I found it to be minus 3 to 4. If we looked at, let's say, minus 5 to 5, it would look like this. And you'd see there's one root right here, but you want to zoom into it. So narrow down your range already. I say go minus 3 to plus 3, which is basically what the bisection algorithm is doing. But you're just getting a better estimate of where to start. So here, let's start with a equals minus 3 and b equals plus 3. So that's the first step. Next step, Let's write it down. Let's do it analytically. Let's get one iteration analytically, and then we'll do another one on Julia. So A, we got -3, and B was 3. Next thing is we go in a loop. So for k equals 1, I do c equals a plus b by 2. So c equals -3 plus 3 by 2, which is 0. Then I will evaluate. So check f of c. That's c. We can do it by hand, or we can just call this function. So we said a equals a plus b by 2 in Julia. And then we said, I want to see f of c. F of c is 3. Is it equal to 0? So in Julia, we found f of c was 3. It is not equal to 0. Then you want to check. Next thing is check f of a times f of c. What does that equal? Well, we can either substitute it ourselves, or we can have Julia do it for us. So we do f of c times f of a. It's negative 126. It's minus 126. Is that less than 0? Right, it is. What does that mean? Well, when it's less than 0, let's go back to our code. Why does that hold true? So for our plot, we had this was A, so this was A1, and this was B1. From that we found our C, which is this, C1. Then we looked at the roots. So f of A1 is here, f of C1 is here. As we expected, f of A1 is negative and f of C1 is positive, means somewhere between those 2 points, we pass the origin, right? Which we know is right here. So we know that the root is between these 2 points, means I don't really need that b that I have here, right? So I can change this b, and now I'm going to look in this interval. So my new updated equation takes this as b2 and this as a2. Between these, so when a2 is -3 and b2, so my a2, let's write that down in there. So we go back here and we say we found this to be negative, and then we said b is equal to c. So b is equal to 3, and then our a is still -3. Next iteration, we do k equals 2, and we get c equals the updated a, which is -3, and the updated b equals c is 0 right here. My bad. So this thing is 0. So updated a, which is -3, and updated c, which is updated b, which is 0 by 2 equals -1.5. Let's not solve it. Let's try to get looking at the graph. We have, this was A2, B2, and then the C2 we found was the midpoint right here, C2. We check f of A2, which is a negative value, f of C2, which is a negative value. Just by looking at it, you can say f of A2 and f of C2 this is negative, this is negative, so this will be greater than 0, right? Which means there isn't a root between these 2 points. Let's check if f of C2 times f of B2 is negative. So this one's negative, this one's positive, this root comes out to be negative, which means that there is a root between B2 and C2. When this is true from our algorithm, we say A2, that our A will become our C, and B will remain the same. So then, this is getting messier, but let's say this point becomes A3, and then this point remains B3. We find another C, which will be somewhere here, and we keep going, right? That's how bisection algorithm works. Now we don't want to do it all by our hands, so we will code it up. We started with A and B, so and so. First thing to check, if there's a root in between, I see if f of A times f of B is negative. Is, let's say, greater than equal to 0 means there isn't a root there. Actually, first thing to do is we'll check if f of A equals 0. If that is the case, then you can just say solution is A, right? Isn't the case for us, but that's how we'll go about it. Else, if f of B is equals 0, then you say solution is B. Correct? And I end it here. Let's see. Yeah, now, check if there's a root in between. There are no roots. Display no roots in this interval. If all of that is true, then we say C equals A plus B by 2. Now we'll go into a looping condition. So we'll say for I equals 1 to, let's say we're going to check 100 iterations at max, right? We say that we already found that there is a root between A and B. So there should be a C in there already. First thing to do, I check f of C if f of C equals 0. If f of C, so let's check the rounded. F of C, comma, digits equals 4 equal 0.0000. Then let's take a variable solution equals nothing for now. And you say that solution equals C. Then you say break. Otherwise, you find out if f of A times f of B is f of C is negative, which means the root is between A and C. Then I say B equals C. Else if f of C into f of B is negative, then I say A equals C. And I update my C equals to the new A plus B by 2. And here goes. If you reach the, then you do end. And if you reach the end of this cell, display, or let's just run it and see what happens. So, are we clear on this? Does this all make sense, the way that we're going about it? So let's check that. Oh, you wanted to display C. Display C. So we found our root to be minus 0.999. Let's see what the value of our function is at this point. It'll take a while. It's really small, right? It's 2.67 to 10 to the power minus 5. So we found a root which was very near to minus 1, which is exactly right. Because we see it should be near minus 1, so it all makes sense. We're good, right? I think in homework, they're going to have you check more conditions and have you write a function of it. But if you understand what's happening here, you should be able to do that as well, right? So that was our bisection algorithm. What we realized in our homework was that when we were doing this plotting, what if I updated my A and B? So let's do it this way. I'm gonna create a plot in here and say display the plot. And our x will be x will go from A to B with intervals of 0.1. It will take a while. It creates new ones. Oh, I forgot the sign. Okay. And then I think we can sleep in here. No magic. That C plus button. It'll probably be really quick. No. Wait. Okay. See this, so let's do that. The way Jeff, I think, was that statement? last statement was? The statement to get a GIF in here. Let's see. I remember nothing. At animate. And then we want to save this animation. I think I need to do like anims. Forget it. Let's forget it. Let's just plot it normally. I'll put a GIF in there once I actually have a chance to worry about it. So, here's what I'm going to do. I'm going to print out my A and B. Stupid. Okay. So first one is from -3 to 0.0. Looks like that. Then the next one, let's take the last one. The last A is -1.00. And the last B is -0.9843 something. And you're going to want smaller steps in there. That does not look right. Oh, you want your axes to be better. X range, excellent, equals between -1.0 and -0.8. It should be a line that goes from -1 point, let's make it 5. And that was too much. Maybe like that. So we see that we can zoom in on this section and it basically becomes a line, right? Which is where we get the intuition that we could have just solved for the solution from this equation instead of looking here and there. Our C is probably around here. What we can do is we can estimate the equation of this line because we know this, we know A, so we know, this one, yeah. We know our A point, which is somewhere here, and we know the B, which is somewhere here, and we know the Y points, which is F of A and F of B. We know the slope of such a line is F of B minus F of A divided by B minus A. And any point on this line, let's say this is somewhere the midpoint C, any point on this line can be given as y minus y y minus the y coordinate at c, which is f of c is equals to m times x minus c, given c is a point on the line with the slope x, right? Slope-intercept form. From here, we're trying to find a solution to the system of equations. So I just put this term equals 0, and I get my c, which the y equals 0. So I get minus f of c equals m times x minus c. From here, I can get my x equals, I think, you'll have to do the math, but minus f of c by m plus c. So what we're trying to do is we're trying to find the point where y is 0, the value of x is this. So that should be our solution. So we update our c according to this rule, which will be our modification to the bisection method. So what becomes, the only change here, when you compare it with our algorithm here, is in our update rule, where we have to do m equals the new slope of the line, and then c is a minus f of a by m. Oh, well, we wanted to take the point a in there. The idea is a comma 0 is a point on the line. So we take these two updations and let's put that in our code instead of doing it normally, and we'll compare the number of iterations. So we had, let's delete this cell and remove this. I'm gonna, we still need all these conditions, but I'm gonna copy from right here. It's the same thing. Paste here, check for the roots, then we update our c with the new rule. So we get the slope m, which is f of b, in the bracket f of b minus f of a divided by b minus a. And then our c is a minus f of a by m. So this becomes a minus f of a by m. We do all the same things here, but then in our update rule, we're gonna update it with the modified algorithm. And then we say display solution. Got the same solution. But was it faster? Well, we can check the number of iterations that this took. Oh, my bad. At the rate show I. At the rate show I. So let's see. I was 9 and I was 1. It found it in the first iteration, actually. Oh, that's probably because our A and B are already calculated in there. So that makes sense. Oops. What did I do? I is 24. Oh, because, oh, that's correct. That's weird. For some reason, this one takes longer. How could that be? What did I do? A is this, C is this. Let's see. Valued at 1.67. This is, this doesn't make sense. Let's put it back to 4. Worse. Okay. So weird. Not updating it right. I guess it's because of the function that I took. So what it's doing is, let's look at this. Basically, the first iteration goes like that, and it says C is around here. Then the next one goes between these 2 points. Takes that C is around here. Then the next one, it needs to do like this. Then it goes like C is around here, which is a lot slower than when you're doing bisection. So I guess sometimes it's better to not start from the modified and only take the modified algorithm approach if you see that your step size is too close. So if B minus A is less than some value, I don't think we're taught this way, but practically, if B minus A is small, so if you're in the smaller interval, then use the modification instead of using it throughout, because that's not going to be the best always. Like, if that was more confusing, let's look at the example in book. I feel like that was a good example. Bisection, here, right here. So we probably don't want to do it anytime before step 4. If we do it continuously, it may not be the best approach. We only want to do it when our system of equations is already linear. If it's too nonlinear and you're drawing a line, trying to find a solution, that isn't the intention. Does that make sense? Yeah? The modified wasn't better, but it'll still find a solution in a reasonable amount of time. Right here? Yeah. Yeah. So we did bisection, we did modified bisection. Next thing is we want to do Newton's method. So what Newton did, he looked at this approach that we took for the modified method. And he said, well, looks like it's better to linearize a solution and then try to find an analytical solution for our system. So we get this point, and we were doing, oh, let's do this. He said, like the problem that we faced why the modification wasn't better is because the step size was too big. So A minus B was way too big, so it didn't make sense. So Newton corrected us, and he went like, well, you only want to look at local slopes. So he said, let's start from your best first guess. So let's say my best guess is minus 2.3, it looks like. So I start from here, and he says, you're going to go in the direction of your gradient. So I look at this, and I say, and he's that my slope is this. He said, if you're here at point x naught, and this is your slope, x naught comma f of x naught, then your updation should be such that x1 equals x naught plus some delta x. And this delta x should be this value in the direction of the gradient. And as long as you're doing that, you're going to be on your way to finding the solution. So if you keep doing that, we get to that point. This is my x1. I take another gradient. I get this point. I take another gradient. I get this point. I take the gradient here. This one, take the gradient here. Get this one, take the gradient here. Get this one. And that's the solution. Does that make sense? That's the intuition behind Newton's method. We're just following our gradient, and we should end up at a root. Let's say you started here. You have the same thing. You'll go like that, then like that, then like that, so and so, but it'll be a longer way. So it depends on your initial point. If your initial guess is way far off, you may never converge, right? But if your initial point is reasonable, you're closer to the goal, you just want to get the exact solution, then Newton is the way to go. So let's see what that means for us. So we have the pseudocode is basically we want to define a starting point, which we're calling x naught. Then you want to compute the gradient, which gave us the direction in which we want to move. And that gradient is given by del f by del x. For this solution, because f is this, the del f by del x will be a scalar. So we can just update our next guess. This will be x1. So what we're doing is we have an x naught. Then you have a differential. You have dx, a df by dx at the point x naught. You use this, and you have f of x naught. You use this to compute x1 from this equation. So we know this from here. We know f of x from here. And we know xk is x naught. Take all these terms, put them in this equation, and we get x1. From x1, again, you have df by dx of x1. And you have f of x1. And you keep going until some f of n, or f of xn, which is approximately 0. So let's see. Let's do by ourselves. For k equals 0. I'm going to take, for this function, my initial guess is, let's say, minus 2. We know the answer is around minus 1, right? Let's take minus 2, and that becomes your x naught. Next thing is, we're going to cheat a little bit, and instead of computing the gradient numerically, let's compute the gradient analytically. For df by dx, if we know differentiation, that's 3x squared minus 4x, right? And then this is at any x. So we're going to build a table like we did for homework, I think. K equals 0, we have x0. Then we want to define, there's an xk, let's say xk, there's a df by dx at xk, and there's an f of xk, right? That's what we have. Cool. And for k equals 0, we have x0, which we took to be minus 2. What is df by dx? Well, we put minus 2 in here. So df by dx at x0 is 3 times minus 2 squared minus 4 times minus 2. That becomes, I think, 12 plus 8 is 20. So this is 20. And f of x naught is minus 2 to the power 3 minus 2 times minus 2 squared plus 3, which is, I think, minus 8 minus 16 plus 3. It should be minus 21, I think. This becomes minus 21. Now for k equals 1, we do the update. So update rule. Right? We say x1 equals x naught plus df by dx at x naught times f of x naught. X naught is minus 2, df by dx at x naught is 20, times f of x naught is minus 21. And probably did something wrong in my calculations because that looks like a big number. Oh, it had to be 1 upon. This thing is. So, my bad. That one is minus 21 by 20. I don't know what that is, but we can check in Julia. So, right here, I want to see what do we have? Minus 2 minus 21 by 20. What do we get? Minus 3.5, minus 3.05. This is minus 3.05. Put it here, get minus 3.05, and then similarly you'll calculate d by dx of x1 and f of x1. And we stop when f of xn is approximately 0. Now, because we understand how to do it by hand, there's a way that we can do it in code, and let's see how that would be. So we have the function f, which is the same as before. Let me just copy it again. So we have the function f, it's the same function. I'm going to define df of x to be the differential of that. So that becomes 3 times x squared minus 4 times x. And now we want to go, we want to initialize an initial point, which we took to be minus 2. The next step, so the first step we did, we initialized, we got an x0 in there. Now you want to be in a loop doing this updation until you find f of x equals 0. So let's initialize solution is an empty vector. For I equals 1 to 100, I look at if f of, let's say, x equals x naught for now. So if f of x, and let's get this whole thing. F of x is about equal to 0, then solution is equal to x. Show the number of iterations and also break, which means you found the solution. If you did not find the solution, then you want to update your x to be x minus f of x divided by df of x, right? Do an end here, and that should be it. That was not it. I forgot a bracket in there. It's probably it. Yeah, got a bracket again. What line? Line 8. Round. That's okay. Oh, and it never found a solution. Because did I have the differential line? Square minus 4x, correct, of x. Solution is equals x, and then you update x like that. X is x plus. And okay, let's first check if df is working. So df of x0. Let's see, df of x0 is 20. That's good. Is x plus, yeah, okay, forward, right, check. X, why would it not date? Got stuck on the local direction. Yeah, I forgot the minus sign. This x is minus 1.35. Let's see. Minus 1.35. Minus x is oh, f of x equals 0 at some point. That's where the solution will break. So, when does this equal 0? Okay, then you want to take another starting point. Let's say I take 0. Yeah, that would be worse. Let's say I took minus 1.5. Yeah, that's what happens when your solutions are, when your differential is 0 at a point. It's probably, oh, it's not 0. Why isn't it updated? Oh, my bad. Damn. That is why you shouldn't code like that. Oh my god. X equals x naught. I was initializing it every loop. Makes sense. So we got it in 5 iterations, which is better than bisection, I think. Yep, better than bisection. It's better than modified bisection. I mean, it's an alternate method. There's sometimes, so here our solution was faster because we analytically knew the differentiation. If sometimes your function is really heavy and calculating a differential is more expensive computationally, sometimes the trade-off is such that bisection will help, but most of the times it's not good. Like computation of your differential, we either do it analytically or it ends up being a way that this one's faster. So we end up using Newton's more, and it's a more generally accepted standard. Right? Like a stupid error in there, but we're here now. So that was Newton's. Do you have questions on that? Can we move on? Because if we understand this, then we can get into Jacobians and vectorizing Newton-Raphson and stuff. Yeah? So, Newton-Raphson. Newton-Raphson is basically the vectorized solution of our Newton's method. So again, our update rule is x plus x, xk plus 1 is some xk plus delta x. There's 3 steps to do. We want to compute our Jacobian numerically. We can do it with all the 3 difference methods. Then you want to find the solution to this equation, where this translates to something like ax equals b, which is the solution of equations that we know. A is this, bx is this, and then your b is this. We know how to solve for this. We've seen it in LU factorization or using QR. Then once we know our unknown, which is delta xk, we know the update. We update our x using this update rule, and we keep doing this until f of x equals 0. So let's say you have a function in R3. So your x is then x1, x2, x3. And this will be your f of x. The first thing to do is you want to create an x naught. So I'm going to make my x naught equals, what do I do? I think my x naught is minus 3.3 and 2. So it's minus 3, 0.3, and 2. Next thing is I want to calculate my differential at x naught. So I want to do df by del x1 at x naught, then del f by del x2 at x naught, and del f by del x3 at x naught. Do we know how to do this? Yes, we do. Let's say we're going to use the symmetric differentiation, because in this case, even though it's easy to get an analytical differential, because we don't have time to do it both ways, we're going to do it numerically like we did in class. So del f by del x1 at x naught will be my function f at x naught plus h times e1 minus f of x naught minus h times e1 by 2h. Now, what does this mean? This means, let's break it down into a different part of the problem. So this thing right here, I'm going to write that down as f of x naught, so x naught is minus 3, 0.3, 2, plus h times e1, that becomes h, so that's the first term. So what it's basically doing is, if you're finding your f, finding the partial differential of x with respect to the first variable x1, then you want to perturb the variable x1 by h. So only the first term is added h and also will be subtracted by h. And that's how we will get the first differential. And then our Jacobian that is df by dx at x naught is just a column-wise concatenation of these elements. So this one will be df by dx at x naught, df by dx2 at x naught, and df by dx3 of x naught. The same way, if you were to write this one down, you would have 1 by 2h, and this thing will become f of x plus, if you want to write it in a more readable way. So let's do f of x naught, which is minus 3, 0.32, and then you do nothing here, and plus h minus f of minus 3, 0.3 minus h, and 2 divided by 2h, and so on. Once we understand how to get the Jacobian, we understand we got this term, we have this term, and we also know f of x. We can find out delta x. So let's try and code this thing up, because doing this by hand is going to be way too much, right? It's too many calculations. We don't want to do that. So here's what we do. I already have the backward and forward subfunctions in here. I defined the function f that we will use directly. And next thing is I want to get a function called calculate Jacobian using forward difference method, right? This function will take our function f and a vector x naught and a value h. And I'm going to use the symmetric differentiation. So the diff value, first thing is we want to iterate over all our columns, right? So first thing is I want to get n equals the size of x naught, number of rows is 1. Then I want to do, there's n variables. So here in this case there were 3, df x1, x2, x3. For I equals 1 to n, you want to loop over all the different variables. So we have the matrix Jacobian equals, let's say zeros n comma n. So Jacobian of the ith column of our Jacobian will be equal to, how do we get the ith column from this? Well, the ith column is f of x naught plus h ei, correct? So that becomes, oh, you want to get the identity matrix as well. So let's get my identity matrix is zeros n comma n plus I. So you want to get the function of x naught plus h times the ith column of the identity matrix minus f of x naught minus h times ith column of the identity matrix, and divide this by 2 times h, and that's your Jacobian. Let's see, there's an error. So we got the function. So let's say at x naught with h equals 0.1, if I want to see my Jacobian, of the function f, x naught, and h. F is not defined. What? F is right here. I didn't run it. H equals my capital I. I wanted to see if return Jacobian. And that's your Jacobian at f of x naught. So now we know the Jacobian. That gives us the del f and del x. Let's copy our code from the Newton's method, which was this one right here. You have an x naught, and you don't have a solution yet. Okay. We're right here. And we had x equals x naught. We found f of x equals, instead of this, we're going to need something like is approx f of x comma 0.0. And error tolerance equals 0.01. And then our update rule changes where x equals x minus df, and in vector terms, this becomes f of x into, actually, this becomes inverse of the Jacobian. Calculate Jacobian times f of x. Let's see. No method matching is approx. And zeros. Size of x. My bad. Inverse algebra. You're using it. Oops, I forgot to pass arguments. So you want to give it f and x and h. And printed too much stuff in there, but this is our answer. And let's see what f of x is. Oh, that's not it. Why do I need this? Yeah, don't need to switch coding.